Subscribe to the channel so you don't miss out on any of these videos. The vastness of space is humbling, filled with mysteries that challenge everything we think we know about reality. But what if I told you the biggest mystery of all isn't in a distant galaxy or hiding behind a black hole? It's something we live with every second of our lives. I'm talking about time itself, and how it's inseparably linked to space. Imagine this: time isn't some universal constant ticking away evenly everywhere. Instead, it bends, stretches, and slows depending on where you are and how fast you're moving. Doesn't that make you wonder how much of our reality we actually understand? To unravel this, we have to dive deep into one of the most revolutionary ideas in human history: Albert Einstein's theory of relativity. This theory didn't just change physics. It fundamentally altered how we think about existence itself. Einstein showed us that space and time aren't separate. They're two sides of the same coin, woven together into what we now call spacetime. And this discovery has implications so strange, they sound like science fiction. But they're not. They're real. So, what does it mean to say space and time are connected? Imagine space as a giant, flexible fabric, like a stretched-out sheet. Every planet, star, and object in the universe sits on this fabric, creating dips and curves. Now imagine time running alongside this fabric, inseparable from it. When something heavy, like a planet, creates a curve in the fabric, it doesn't just bend space, it bends time, too. This is why time moves slower near massive objects like black holes or even Earth compared to outer space. The very flow of time depends on gravity and speed. This phenomenon, known as time dilation, has been proven again and again. For instance, astronauts aboard the International Space Station age just a little bit slower than we do on Earth because they're farther from the planet's gravitational pull. It's not much, fractions of a second, but it's real. And the faster you move through space, the slower time moves for you. This isn't just a theory, it's been confirmed with atomic clocks on airplanes, satellites, and even GPS systems. Your phone's GPS wouldn't work if we didn't account for time dilation. But let's zoom out a bit. Why does this even matter? How does this strange connection between time and space impact us? Well, it's not just a curiosity for scientists. It's a roadmap for space exploration. If we're ever going to reach distant stars or explore other galaxies, we have to understand how time behaves in space. Let's say we figure out how to travel near the speed of light, a speed Einstein says is the universal limit. For the astronauts on board, time would pass much slower than for those of us back on Earth. If they spent a few years traveling to a nearby star, they might return to find that decades or even centuries have passed here. This isn't just a cool idea. It's a consequence of how the universe actually works. And then there's the question of black holes, which are like laboratories for testing Einstein's ideas. These cosmic monsters are so dense, their gravity warps spacetime to an extreme degree. If you were to hover near the edge of a black hole, what we call the event horizon, time for you would almost stop compared to an observer far away. This effect, called gravitational time dilation, shows us just how flexible time can be. But it also raises unsettling questions. If time can stretch and slow, could it stop altogether? Could we manipulate it? Could we reverse it? These questions take us into the realm of theoretical physics, where ideas like wormholes and time travel start to feel almost possible. Wormholes, for instance, are hypothetical tunnels through spacetime that could connect two distant points in the universe. Some theories suggest they might even allow us to move backward or forward in time. But before we get ahead of ourselves, let's not forget the challenges. Wormholes, if they exist, might be so unstable that they'd collapse before anything could pass through them. Or they might require something exotic, like negative energy, to stay open. But here's where it gets even weirder. If spacetime can bend, stretch, and twist, does that mean the universe itself has a beginning and an end? Einstein's equations suggest that spacetime is dynamic. It can expand, contract, and evolve. This ties into the idea of the Big Bang, where space and time themselves came into existence. Before the Big Bang, there wasn't just no space. There was no time. Think about that for a second, a time when time didn't exist. It's a concept that breaks our brains because we can't imagine a reality without time. Now, let's bring this full circle. If space and time are interconnected, how does this relationship affect our everyday lives? It might seem abstract, but we're already relying on it. Your smartphone's GPS system, for example, uses satellites that orbit the Earth. These satellites experience both gravitational time dilation, because they're farther from Earth's gravity, and velocity-based time dilation, because they're moving fast. If engineers didn't adjust for these effects, your GPS would be off by miles. And that's just one application. As we venture deeper into space, understanding spacetime will become even more crucial. Consider interstellar travel, where distances are so vast that even light takes years to cross them. The concept of time dilation means that if we could travel close to the speed of light, a trip to a distant star might feel short to the travelers, even though centuries pass on Earth. But this raises profound questions. If humanity ever becomes a spacefaring civilization, how will we deal with the fact that space travel could essentially make astronauts into time travelers? They might leave on a mission and return to find their world unrecognizable. And then there's the ultimate question: could we ever manipulate spacetime itself? Scientists are exploring concepts like warp drives, which would compress spacetime in front of a spacecraft and expand it behind, allowing faster-than-light travel without actually breaking the cosmic speed limit. While these ideas are still in the realm of theory, they're grounded in real physics. But they also come with challenges, like the need for enormous amounts of energy. The more we learn about the relationship between space and time, the more questions arise. Could there be places in the universe where spacetime behaves in ways we can't even imagine? Could the laws of physics themselves vary across the cosmos? And if time is flexible, could it someday be harnessed, controlled, or even reversed? These are the mysteries that keep scientists awake at night, and they remind us how much we still have to learn about the universe we call home. The mystery of time and space doesn't just stretch across the stars. It reaches into the very foundations of reality itself. To continue, let's unravel how time dilation impacts not only space exploration but our very understanding of the universe's structure and history. One of the most fascinating aspects of time dilation is how it reveals the relative nature of time. To someone moving at near light speeds, time slows down dramatically compared to someone standing still. This idea is at the heart of Einstein's special theory of relativity. Imagine a spacecraft traveling to a star system 10 light-years away at 90% the speed of light. For those on Earth, the journey would take about 11 years considering acceleration and deceleration. But for the astronauts on board, the trip might feel like just a few years. This effect is due to the way spacetime stretches and contracts depending on motion, a phenomenon so counterintuitive that it continues to baffle even seasoned scientists. The implications of this aren't just theoretical. They challenge fundamental ideas about cause and effect, past and future. If time can slow down or speed up depending on movement and gravity, does this mean that the order of events is subjective? Could two observers in different parts of the universe disagree about what happened first? This is more than a philosophical question. It's a real problem for scientists trying to piece together the universe's timeline. Take the age of the universe, for instance. We estimate it to be about 13.8 billion years old based on observations of the cosmic microwave background radiation, the faint glow left over from the Big Bang. But this measurement assumes a universal clock, ticking evenly across all of spacetime. If time isn't constant, as relativity shows, could different parts of the universe experience time differently? What would that mean for our understanding of cosmic history? Now, let's dive deeper into gravitational time dilation, which occurs near massive objects like black holes. A black hole's immense gravity warps spacetime so severely that time slows to a crawl near its event horizon. If you could observe someone falling into a black hole from a safe distance, they'd appear to slow down and eventually freeze in time just before crossing the event horizon. Meanwhile, for the person falling in, time would feel normal, until they were crushed by the black hole's singularity, a point of infinite density where spacetime itself breaks down. This extreme warping of time isn't just a theoretical concept. It's been observed indirectly through phenomena like gravitational lensing, where light from distant stars bends around massive objects like black holes. By studying these effects, scientists gain insights into how spacetime behaves under extreme conditions. But black holes also pose deeper questions. Could they be gateways to other parts of the universe? Or could they lead to entirely different universes? These are the kinds of questions that push the boundaries of relativity and venture into the realm of quantum mechanics. Quantum mechanics, the study of the very small, seems to contradict many of the principles of relativity, which governs the very large. For instance, while relativity treats spacetime as smooth and continuous, quantum mechanics suggests that on the smallest scales, spacetime might be made up of tiny, discrete units, like pixels on a screen. Reconciling these two views is one of the biggest challenges in modern physics. And time lies at the heart of the conflict. Some theories, like string theory, attempt to bridge the gap by suggesting that spacetime isn't fundamental but emerges from more basic entities, vibrating strings of energy. If true, this would mean that time itself is an illusion, a byproduct of deeper physical processes we don't yet understand. This idea is as mind-bending as it sounds. It suggests that the flow of time, which feels so real to us, might be no more fundamental than the sensation of heat or the color of the sky. But what does this mean for space exploration? If time isn't a fixed constant, how can we plan missions to distant worlds? For one, it means we have to account for the relativistic effects of time dilation, especially as we develop faster spacecraft. It also means rethinking our assumptions about communication and navigation in deep space. If two spacecraft are moving at different speeds or orbiting different planets, their clocks won't sync up. This might sound trivial, but it could lead to massive complications in coordinating missions across vast distances. Speaking of vast distances, let's consider the ultimate goal of space exploration: interstellar travel. If humanity ever hopes to become a multiplanetary species, we'll need to conquer not just the physical distances between stars but the time it takes to traverse them. One possible solution is cryogenic sleep, where astronauts are put into a state of suspended animation for long journeys. But even this doesn't solve the problem of time dilation. If astronauts travel close to the speed of light, they'll return to a world far removed from the one they left, a concept that raises ethical and psychological challenges. How do you prepare someone to return to a society they no longer recognize? And how do you ensure that society is still there when they return? The psychological effects of time dilation aren't limited to spacefarers. They also affect our understanding of ourselves and our place in the universe. If time is relative, what does that mean for our memories, our experiences, and our identities? These questions aren't just academic. They touch on the deepest aspects of what it means to be human. And then there's the question of time travel. While time dilation allows for a kind of one-way travel into the future, traveling back in time is a far murkier prospect. Some solutions to Einstein's equations, like the Kerr metric for rotating black holes, suggest that closed time-like curves, essentially loops in spacetime, might allow for backward time travel. But these solutions often require conditions that may not exist in our universe, like negative energy or exotic matter. Even if time travel were possible, it would create paradoxes, like the famous grandfather paradox. What happens if you go back in time and prevent your own birth? Despite these challenges, the possibility of manipulating spacetime fuels some of the most ambitious ideas in physics. Could we harness the energy of black holes or wormholes to create shortcuts through spacetime? Could we use advanced technology to slow down time for long journeys, effectively putting astronauts into a state of suspended animation without cryogenics? These ideas may sound far-fetched, but so did the idea of flying to the moon just a century ago. The more we learn about the relationship between time and space, the more it feels like we're scratching the surface of something much larger. Time isn't just a backdrop for our lives. It's an active player in the universe's story, shaping everything from the motion of galaxies to the ticking of our own hearts. The intricate relationship between time and space keeps unfolding layer by layer, revealing a reality far more complex and interconnected than we ever imagined. Time, as it turns out, isn't simply a linear progression from past to future. It is deeply tied to space, gravity, motion, and even the fundamental fabric of the universe itself. This entanglement is the basis for some of the most mind-boggling mysteries and opportunities in space exploration. Building on the idea of time dilation and the warping of spacetime, let's turn our attention to its implications on the large-scale structure of the universe. One of the key concepts in modern cosmology is the idea of spacetime expansion. Since the Big Bang, spacetime itself has been stretching, causing galaxies to move away from one another. This expansion isn't uniform. It's influenced by dark energy, an enigmatic force that accelerates this stretching. But here's the twist. As spacetime expands, it also stretches the perception of time. Distant galaxies appear to us as they were billions of years ago because their light has taken that long to reach us. But because of the universe's expansion, that light is redshifted, meaning its wavelength has been stretched, altering how we perceive time passing in those distant regions. From our vantage point, it seems like time in far-off galaxies is moving slower. This isn't just an illusion, it's a real effect of the relationship between time and the expanding fabric of space. This phenomenon allows scientists to effectively look back in time, peering into the universe's infancy by studying ancient light, like the cosmic microwave background radiation. Let's bring this back to the ground level, so to speak. If the universe's expansion can warp time and space on a grand scale, what happens on smaller, localized scales, like around planets, stars, or black holes? This is where gravitational time dilation plays a crucial role. Time runs slower in stronger gravitational fields, a concept first tested during the famous Pound-Rebka experiment in 1960, which measured the tiny differences in the passage of time at different heights on Earth due to gravity. The experiment confirmed Einstein's predictions with astonishing precision, laying the groundwork for technologies like GPS. You might wonder, how does GPS relate to time dilation? The satellites orbiting Earth experience both forms of time dilation, special relativity due to their high speeds and general relativity because they are farther from Earth's gravitational pull than people on the surface. Without accounting for these effects, GPS systems would drift by about 10 kilometers per day, making them completely unreliable. This real-world application is a striking example of how understanding the relationship between time and space impacts daily life, not just theoretical physics. When we think about space exploration, these relativistic effects take on even greater significance. Imagine a future where humanity embarks on interstellar journeys. For a spacecraft traveling at relativistic speeds, time for the crew would pass much more slowly than for those left behind on Earth. This creates a kind of one-way communication problem. Astronauts would return to find that decades, perhaps centuries, had passed back home. What would this mean for maintaining connections with loved ones, or for preserving historical continuity? Science fiction often explores these dilemmas, but they are grounded in real physics. Movies like Interstellar dramatize how time dilation affects personal relationships, showing astronauts aging slower than their families on Earth. While Hollywood takes creative liberties, the core idea is scientifically accurate. The closer you are to a strong gravitational field, like that of a black hole, the slower time moves for you relative to someone farther away. This creates a disorienting yet fascinating disparity in the experience of time, a phenomenon that space explorers may one day face firsthand. The mysteries deepen when we consider how time might behave in the most extreme environments in the universe. For instance, near the event horizon of a black hole, the warping of spacetime is so intense that time almost comes to a standstill from an external observer's perspective. Theoretical physicists speculate that if you could somehow survive the journey past the event horizon, you might experience time in entirely different ways, or even encounter phenomena like wormholes, theoretical shortcuts through spacetime. Wormholes are a particularly tantalizing concept because they suggest the possibility of faster-than-light travel, or even time travel. According to Einstein's equations, a wormhole could connect two distant points in spacetime, allowing you to traverse vast cosmic distances in an instant. The catch? Wormholes would require exotic matter with negative energy density to remain stable, something we've never observed or created. But even the theoretical existence of such structures raises profound questions. If we could manipulate spacetime to create a wormhole, could we also use it to send information, or people, backward or forward in time? This brings us to the broader question of whether time travel is truly possible. While Einstein's relativity allows for theoretical scenarios involving closed time-like curves, practical time travel faces enormous hurdles, not least of which are the paradoxes it creates. For example, if you travel back in time and change the past, do you create a new timeline? Or does the universe somehow prevent you from altering events, as some interpretations of quantum mechanics suggest? These questions straddle the boundary between physics and philosophy, inviting endless speculation. Beyond time travel, the interplay of time and space also influences our understanding of the universe's ultimate fate. If dark energy continues to drive the acceleration of the universe's expansion, space-time could stretch so much that galaxies, stars, and even atoms are torn apart in a scenario known as the Big Rip. Alternatively, if dark energy weakens over time, the universe might eventually stop expanding and collapse back into a singularity in a Big Crunch. Each possibility carries profound implications for the nature of time. Would time itself cease to exist in a collapsed universe? Or would it loop back on itself, creating an eternal cycle of creation and destruction? As we explore these cosmic questions, it's clear that the relationship between time and space isn't just an abstract curiosity. It's the key to unlocking the universe's deepest secrets. The interplay of motion, gravity, and space-time shapes everything from the behavior of black holes to the flow of time in our everyday lives. By continuing to study these phenomena, we not only expand our understanding of the cosmos but also confront the very nature of reality itself. The profound relationship between time and space continues to reveal itself through the lens of relativity and beyond. It's not just a theoretical framework, it's a guide to understanding the cosmos and our place within it. As we delve deeper, the implications for space exploration, the fate of the universe, and even the nature of existence grow more extraordinary. One of the most captivating aspects of time and space is how they interact at the quantum level. Quantum mechanics, the science of the very small, often seems to clash with general relativity, which governs the very large. Yet both must coexist to fully explain the universe. This dichotomy brings us to the concept of quantum spacetime. At the Planck scale, the smallest scale conceivable, spacetime might not be smooth and continuous but instead composed of tiny, discrete units, like pixels on a screen. These quantum fluctuations could create a foamy structure, where time and space blur into something fundamentally different from our everyday experience. The search for a theory of quantum gravity, one that unites quantum mechanics and general relativity, is among the greatest challenges in modern physics. One promising avenue is string theory, which posits that all particles are actually tiny vibrating strings of energy. These strings exist not just in 3 dimensions but in up to 11 dimensions of space-time. In this framework, the fabric of space and time itself could be a result of string interactions, potentially explaining how time emerges from a deeper, more fundamental layer of reality. What does this mean for our understanding of time dilation and space-time curvature? If space-time is quantized, the effects of gravity on time could operate differently at microscopic scales. Experiments using advanced particle accelerators or space-based observatories could one day reveal subtle deviations from Einstein's equations, offering clues about the quantum nature of time. Such discoveries would revolutionize our understanding of the universe and open up new possibilities for manipulating spacetime in ways we can barely imagine. Let's shift focus to a phenomenon that bridges the quantum and cosmic realms: the nature of black holes. Black holes are extraordinary laboratories for studying the relationship between time and space. Their immense gravity warps spacetime to extremes, creating effects like gravitational lensing, where light bends around the black hole, and time dilation so intense that time virtually halts at the event horizon. But what happens inside a black hole? According to classical general relativity, the core of a black hole contains a singularity, a point where density and gravity become infinite, and the laws of physics as we know them break down. Time and space as we understand them cease to exist. However, quantum theories suggest that this singularity might be avoided, replaced instead by a quantum fuzz, or a bouncing loop of spacetime. Some theories even propose that black holes could act as gateways to other universes or serve as incubators for new Big Bangs, where time begins anew. The possibility of multiverses, a collection of parallel universes, adds another layer of intrigue. If multiple universes exist, each with its own space-time fabric, how do their timelines interact? Are they entirely independent, or could they influence one another through phenomena like quantum entanglement? These questions are at the cutting edge of theoretical physics, challenging our notions of causality, continuity, and time itself. Space exploration, too, is profoundly shaped by these insights. Missions to distant stars or planets must account for relativistic effects, especially as we develop faster propulsion systems. If humanity ever achieves near-light-speed travel, the time dilation experienced by astronauts could redefine space exploration. For instance, while only a few years might pass for the crew, centuries could elapse on Earth. This time gap would require new approaches to mission planning, communication, and even the psychology of long-term isolation. Consider, for example, the concept of generation ships, self-sustaining spacecraft designed to house multiple generations of humans during interstellar journeys. While the crew aboard might experience a few decades of travel, their destination could be thousands of years into the future. What kind of society would emerge in such an environment? How would the perception of time, history, and progress evolve when daily life aboard the ship is detached from the world left behind? Beyond human exploration, the time-space relationship also influences how we study the universe remotely. Telescopes like the James Webb Space Telescope allow us to peer into the past by capturing light that has traveled billions of years across expanding spacetime. These observations provide glimpses of galaxies, stars, and phenomena that existed shortly after the Big Bang. Yet, as we observe these ancient events, we're also constrained by the speed of light and the curvature of spacetime. Advanced technologies, such as gravitational wave detectors, offer new ways to probe the universe, potentially revealing secrets about its earliest moments or uncovering hidden dimensions. As we examine the far reaches of spacetime, we're also forced to confront the possibility of cosmic censorship. This principle suggests that the universe hides its most extreme phenomena, like singularities, behind event horizons or other boundaries. If true, it means there are aspects of time and space that will forever remain inaccessible to us, no matter how advanced our technology becomes. This limitation challenges our quest for knowledge, raising philosophical questions about the nature of reality and our ability to understand it. But perhaps the most profound mystery of all lies in the nature of time itself. Is time an objective feature of the universe, or is it a construct of human perception? Some physicists argue that time might be an emergent property, a byproduct of deeper, timeless processes. If this is true, then our understanding of past, present, and future could be fundamentally flawed. Time might not flow but instead exist as a block universe, where all moments coexist simultaneously, and the passage of time is merely an illusion created by our consciousness. This idea has profound implications for how we view causality, free will, and the nature of existence. If all moments are equally real, then every decision we make, every event we experience, is already written into the fabric of spacetime. Yet, our perception of time's flow gives us the illusion of choice and progression. Reconciling this paradox is one of the greatest challenges in both physics and philosophy. As we continue to explore the cosmos, we're not just uncovering the mysteries of space and time, we're also confronting the limits of human understanding. The relationship defined by relativity is just the beginning. The deeper we delve, the more we realize how interconnected and enigmatic our universe truly is. And perhaps, in the quest to unravel these mysteries, we'll discover not just the secrets of spacetime but also the answers to the most profound questions about ourselves. The exploration of space and time not only pushes the boundaries of science but also reshapes our fundamental understanding of reality. While we've delved into relativity, quantum mechanics, and black holes, there's more to uncover about how these concepts influence the universe and our existence within it. One of the most fascinating aspects of spacetime lies in the concept of cosmic expansion. Edwin Hubble's groundbreaking discovery in the early 20th century revealed that galaxies are moving away from us, and the farther they are, the faster they recede. This observation led to the understanding that the universe is expanding, and with it, space-time itself is stretching. This phenomenon directly ties into the relationship between time and space because as the universe expands, it alters the way we perceive and measure both. Cosmic expansion gives rise to the concept of the cosmological horizon, a boundary beyond which we cannot see because light from those regions has not had time to reach us due to the universe's finite age. This horizon is not static, it evolves as the universe ages and expands. As a result, the relationship between space and time is inherently dynamic. What lies beyond this horizon remains one of the greatest mysteries of modern cosmology. Could there be other universes, different laws of physics, or a vast emptiness stretching indefinitely? Each possibility reshapes how we conceptualize time and space. An extension of cosmic expansion is the idea of the Big Rip, a theoretical end of the universe where space-time itself is torn apart. In this scenario, dark energy, a mysterious force driving the acceleration of the universe's expansion, continues to grow in strength. Over billions of years, it could eventually overpower all other forces, tearing apart galaxies, stars, planets, and even atoms. Time, as we know it, would cease to exist because without a structure to measure change, the concept of time loses meaning. This dramatic end underscores the fragility of space-time and the profound effects of cosmic forces on its structure. Let's now consider another enigmatic phenomenon tied to space-time: wormholes. Wormholes, or Einstein-Rosen bridges, are theoretical shortcuts through space-time that connect two distant points. If they exist, they could revolutionize space travel, allowing instantaneous journeys across vast cosmic distances. However, the nature of time within a wormhole is equally fascinating. Depending on the configuration, a wormhole could act as a time machine, enabling travel into the past or future. This possibility opens up a Pandora's box of questions about causality, paradoxes, and the nature of free will. For instance, what happens if you travel back in time and change an event? The classic grandfather paradox suggests that altering the past could create logical inconsistencies, such as preventing your own existence. Some physicists propose solutions like the Novikov self-consistency principle, which states that any actions taken by a time traveler are already part of history and cannot alter the past. Others suggest that changes could create parallel timelines or alternate universes. These ideas, while speculative, highlight the deep interconnectedness of space, time, and causality. The search for wormholes or evidence of their existence is ongoing, with no definitive answers yet. However, the study of exotic phenomena like these expands our understanding of space-time and its potential applications. It also reinforces the idea that our current knowledge represents only a small fraction of what's possible, and the universe likely holds surprises far beyond our imagination. Another intriguing topic is the arrow of time. While the laws of physics are largely time-symmetric, meaning they work the same forward and backward in time, our experience of time is directional. We perceive time as flowing from the past to the future, an asymmetry known as the arrow of time. This directionality is closely tied to entropy, a measure of disorder. According to the second law of thermodynamics, entropy tends to increase in an isolated system, giving time its forward progression. Yet, this raises profound questions. Why did the universe start in a state of low entropy? What governs the progression of time, and could it ever reverse? Some theories suggest that at the Big Bang, the universe split into two time directions, with one flowing forward, our universe, and the other flowing backward. This bidirectional model of time challenges our conventional understanding and suggests that our perception of time may be only one facet of a more complex reality. Time and space also intersect intriguingly in the study of gravity waves, ripples in space-time caused by massive cosmic events like colliding black holes or neutron stars. These waves travel at the speed of light, stretching and compressing space-time as they pass. Detected for the first time in 2015 by the LIGO Observatory, gravitational waves offer a new way to observe the universe. Unlike light or electromagnetic waves, they can pass through matter undisturbed, providing insight into phenomena hidden from traditional telescopes. They also confirm predictions made by Einstein's theory of relativity, further cementing the intricate relationship between time and space. The detection of gravitational waves has profound implications for both science and philosophy. It allows us to study cosmic events billions of years in the past, essentially eavesdropping on the universe's history. By analyzing these waves, scientists can learn about the properties of black holes, neutron stars, and other extreme objects, shedding light on how they warp spacetime. The study of these distortions could eventually lead to a deeper understanding of the fabric of the universe and even the mechanisms behind its creation. Finally, let's consider the implications of these ideas for humanity's future. As our understanding of time and space deepens, so too does our ability to manipulate them. Theoretical concepts like warp drives, which bend spacetime to allow faster-than-light travel, are being studied as potential technologies. While still in the realm of speculation, such advances could make interstellar exploration a reality, opening up new frontiers and possibly leading to encounters with extraterrestrial civilizations. Moreover, the philosophical questions raised by our exploration of spacetime will continue to shape our worldview. What does it mean to exist in a universe governed by such intricate and mysterious laws? How do our perceptions of time and space influence our understanding of life, death, and purpose? As we grapple with these questions, we're not just studying the universe, we're also redefining what it means to be human. The journey into the mysteries of time and space is far from over. With each discovery, we take another step closer to unraveling the ultimate nature of reality. Yet, the more we learn, the more questions arise, ensuring that this quest will continue to inspire and challenge us for generations to come. The intersection of time and space, as defined by relativity, introduces ideas so profound that they challenge the very framework through which we perceive reality. While our exploration has touched upon concepts such as time dilation, gravitational waves, and the arrow of time, there is much more to uncover about how these phenomena manifest in the universe and affect both theoretical understanding and practical applications. One particularly captivating aspect of spacetime is the phenomenon of cosmic voids and their impact on our understanding of the universe. Cosmic voids are vast, empty regions in the cosmos where galaxies are sparse or nearly absent. These voids, spanning millions of light years, represent the dark, uncharted territories of spacetime. Their existence reveals how matter is distributed unevenly across the universe and offers clues about the forces shaping spacetime itself. Interestingly, time behaves differently within these voids compared to regions densely packed with matter. The weaker gravitational forces in voids lead to less spacetime curvature, causing time to pass slightly faster than in regions of higher gravity. This subtle difference in the passage of time, though minuscule on human scales, provides a natural laboratory for studying the effects of general relativity. Observing these time variations could help refine our models of the universe and reveal whether there are hidden forces or particles influencing spacetime. Similarly, the concept of the cosmic web further highlights the interplay between space and time. The cosmic web is the large-scale structure of the universe, consisting of galaxies, dark matter, and gas filaments interconnected like a vast, three-dimensional network. These filaments stretch across billions of light years, with cosmic voids filling the spaces in between. The cosmic web is not just a map of matter, it is a snapshot of how spacetime evolves. The gravitational pull within the web shapes the motion of galaxies, while the flow of time across its structures affects how we observe its growth. On an even grander scale, we encounter the concept of multiverses, which challenges the very limits of spacetime as we understand it. According to certain interpretations of quantum mechanics and string theory, our universe may be just one of countless others existing within a multiverse. Each of these universes could have its own version of spacetime, governed by different physical laws, dimensions, and constants. The multiverse theory raises profound questions about the nature of time and space, including whether they are universal constructs or merely localized phenomena unique to our universe. For instance, if another universe exists with a radically different structure of spacetime, how would time behave there? Would it flow linearly, cyclically, or perhaps not exist at all? Could it be possible for these universes to interact, creating anomalies in our own spacetime? While these questions remain speculative, they highlight the vast scope of possibilities within the realm of spacetime studies. Another fascinating element of spacetime is the role of quantum mechanics. The famous quantum foam hypothesis suggests that spacetime is not smooth but instead fluctuates on incredibly small scales due to quantum uncertainty. This microscopic turbulence could influence the behavior of time and space in ways we cannot yet measure, potentially serving as the bridge between general relativity and quantum mechanics, a unification scientists have been striving toward for decades. Quantum mechanics also introduces the concept of entanglement, where particles separated by vast distances become instantaneously connected. This spooky action at a distance, as Einstein famously described it, appears to defy the limitations of spacetime, as information between entangled particles is exchanged faster than the speed of light. Could this phenomenon hint at a deeper layer of reality where spacetime as we know it becomes irrelevant? Or is entanglement evidence of hidden dimensions that interconnect our universe in ways we cannot yet perceive? Hidden dimensions, often discussed in the context of string theory, propose that spacetime may consist of more than the familiar three spatial dimensions and one temporal dimension. These extra dimensions could be compactified, curled up so tightly that they are imperceptible at human scales. However, their effects might still influence the behavior of particles and forces, potentially offering explanations for unresolved mysteries like the nature of dark energy and dark matter. Speaking of dark matter and dark energy, these enigmatic components of the universe hold the key to understanding spacetime on a cosmic scale. Dark matter, which makes up about 27% of the universe, exerts gravitational effects that help bind galaxies and clusters together. Without it, the large-scale structure of the universe would not exist as we observe it. Yet dark matter does not interact with light or ordinary matter in conventional ways, making it invisible and incredibly elusive. Dark energy, on the other hand, accounts for roughly 68% of the universe and is responsible for the accelerated expansion of spacetime. Its influence permeates every corner of the cosmos, shaping the evolution of time and space itself. Despite its vast impact, dark energy remains one of the greatest mysteries of modern science. Understanding its nature could unlock the secrets of the universe's ultimate fate, whether it will continue expanding forever, slow down and collapse, or reach a state of equilibrium. The study of dark matter and dark energy also leads us to the concept of the Hubble constant, a critical measurement in cosmology that describes the rate of the universe's expansion. However, different methods of calculating the Hubble constant yield slightly different results, leading to what scientists call the Hubble tension. This discrepancy suggests that our understanding of spacetime and its dynamics may be incomplete, pointing toward new physics beyond our current models. One intriguing possibility involves modifying our interpretation of gravity itself. Alternative theories, such as modified Newtonian dynamics, (MOND), or theories of emergent gravity, propose that the effects we attribute to dark matter and dark energy could instead arise from changes in how spacetime behaves on large scales. These theories challenge the traditional view of spacetime as a passive backdrop, instead portraying it as an active, evolving entity. At the heart of all these mysteries is the question of spacetime's origin. How did time and space come into existence? The Big Bang Theory suggests that spacetime began as a singularity, a point of infinite density and temperature, before expanding into the universe we observe today. However, the nature of this singularity remains elusive. Did spacetime emerge from nothing, or was it shaped by pre-existing conditions or dimensions? Could the universe itself be cyclical, with spacetime repeatedly collapsing and rebirthing? As we explore these profound questions, we must also consider the practical implications of our discoveries. Advancements in our understanding of spacetime have the potential to revolutionize technology, communication, and exploration. Concepts like quantum teleportation, spacetime engineering, and advanced propulsion systems may one day become realities, enabling humanity to reach new frontiers and perhaps even transcend the limitations of our own existence. The journey into the mysteries of time and space is one of endless curiosity and discovery. It challenges us to rethink what we know, question what we believe, and imagine what lies beyond. As we continue to unravel the secrets of spacetime, we not only expand our knowledge of the universe but also deepen our appreciation for the intricate, interconnected fabric of reality that binds us all. The intricate dance between time and space continues to captivate scientists, philosophers, and dreamers alike. The mysteries of spacetime stretch beyond theoretical debates and extend into tangible realities that shape our universe and the technology we use to explore it. One of the most practical and fascinating aspects of spacetime is its role in navigation and communication, especially when it comes to space exploration and satellite systems. Take, for example, the Global Positioning System, GPS. This everyday technology relies heavily on our understanding of spacetime. Satellites orbit Earth at high speeds and at altitudes where gravity is weaker compared to the planet's surface. Due to these conditions, two relativistic effects come into play: time dilation from their velocity and gravitational time dilation from their position in the weaker gravitational field. The clocks on these satellites tick faster than those on the ground, but their high-speed movement slows time slightly relative to us. The net effect is that satellite clocks advance about 38 microseconds faster per day than clocks on Earth. While this might seem negligible, even such a tiny discrepancy can lead to navigation errors of several kilometers per day. To ensure GPS accuracy, engineers use Einstein's equations to correct for these spacetime effects. The same principles apply to deep space communication with spacecraft. When we send signals to distant probes like the Voyager spacecraft, the time it takes for these signals to travel is not just a function of distance but also influenced by the curvature of spacetime around celestial bodies along the way. These delays can amount to hours or even days when dealing with interplanetary or interstellar distances, reminding us that spacetime is not merely a theoretical construct. It has real-world implications that directly affect how we interact with the cosmos. Spacetime's influence becomes even more pronounced when we consider black holes, some of the most extreme objects in the universe. Black holes distort spacetime to such an extent that time slows dramatically near their event horizons, the boundaries beyond which nothing, not even light, can escape. The idea of time coming to a standstill at the event horizon, at least from the perspective of an outside observer, exemplifies how spacetime warps under immense gravitational forces. For an astronaut falling into a black hole, however, the experience would be vastly different. To them, time would appear to flow normally as they approach the singularity, the infinitely dense core of the black hole. This paradox, where time behaves differently depending on perspective, underscores the complexity and relativity of spacetime. Black holes also give rise to questions about the fate of information, as their immense gravity seems to erase all traces of anything that falls into them. Yet, recent theories suggest that information might be encoded in the event horizon, hinting at a deeper, quantum-level structure of spacetime. Another extreme example of spacetime distortion occurs in the vicinity of neutron stars, the remnants of massive stars that have undergone supernova explosions. Neutron stars are so dense that a single teaspoon of their material would weigh billions of tons on Earth. This density creates intense gravitational fields that warp spacetime and produce some of the strongest observable effects of relativity. For instance, light emitted from the surface of a neutron star is redshifted, a phenomenon where the wavelength of light stretches as it escapes the star's gravitational pull. Similarly, time slows down for objects near the neutron star compared to those farther away. Observations of these effects provide crucial tests for general relativity, helping scientists refine their understanding of spacetime and its behavior under extreme conditions. These celestial phenomena also have profound implications for our search for extraterrestrial life. If advanced civilizations exist elsewhere in the universe, their perception of time and space might differ significantly from ours, depending on their location and the conditions of their home planet or star system. For example, a civilization near a massive star might experience time more slowly than we do, potentially affecting how they develop technology or perceive the cosmos. This brings us to another intriguing idea: the potential for manipulating spacetime itself. Concepts like wormholes and warp drives, popularized by science fiction, are grounded in real scientific theories, even if they remain speculative. Wormholes, or Einstein-Rosen bridges, are hypothetical tunnels through spacetime that could connect distant regions of the universe. While creating or stabilizing a wormhole would require exotic matter with negative energy, a substance that may or may not exist, the idea remains a tantalizing possibility for future exploration. Similarly, the concept of a warp drive, inspired by physicist Miguel Alcubierre, suggests that it might be possible to compress spacetime in front of a spacecraft while expanding it behind, effectively allowing the craft to ride a wave of spacetime. This approach would enable faster-than-light travel without violating the laws of physics, as the spacecraft itself would remain stationary within its local bubble of spacetime. While these ideas are far from practical realization, they highlight the potential for humanity to one day harness the fabric of spacetime itself. Even without such advanced technologies, our current understanding of spacetime already challenges the limits of human imagination. For instance, the detection of gravitational waves, ripples in spacetime caused by massive objects like merging black holes or neutron stars, has opened a new window into the universe. These waves allow us to observe cosmic events that were previously invisible, providing insights into the most violent processes in the cosmos. Gravitational wave detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, and Virgo have already made groundbreaking discoveries, confirming Einstein's predictions and revealing phenomena like binary black hole mergers. As detection methods improve, we may uncover entirely new classes of events, shedding light on the unseen aspects of spacetime. Moreover, the relationship between time and space extends beyond the cosmos and into the human experience. The relativity of time challenges our perception of reality and forces us to confront fundamental questions about existence. Are past, present, and future truly distinct, or are they merely aspects of a single, unified spacetime? If time is relative, what does that mean for concepts like free will, causality, and the nature of consciousness? Philosophers and physicists alike grapple with these questions, exploring whether time is an emergent property, arising from deeper, more fundamental principles, or a fundamental aspect of the universe itself. Some theories even suggest that time might not exist at the most basic level, with the universe operating as a timeless, interconnected whole. As we delve deeper into the mysteries of spacetime, we not only expand our scientific knowledge but also confront the profound implications of our place in the universe. Time and space, once thought to be simple, independent concepts, have revealed themselves to be the intricate threads of a cosmic tapestry that defies easy understanding. Yet, it is precisely this complexity that drives our curiosity and fuels our desire to explore further. The study of spacetime is more than an academic pursuit. It is a journey into the very essence of reality. It challenges us to rethink our assumptions, embrace uncertainty, and imagine possibilities beyond our current understanding. In doing so, it offers not just answers, but also new questions, reminding us that the universe is far more vast, mysterious, and wondrous than we could ever have imagined. Our exploration of spacetime invites us to consider the immense role it plays in both our understanding of the universe and our potential to explore it further. While we've touched on phenomena like time dilation, gravitational waves, and the curvature of spacetime around massive objects, there's still much more to unpack about how these concepts influence both the theoretical and practical sides of space exploration. To truly grasp spacetime's intricacies, we must delve deeper into its connection to energy, matter, and motion. One cornerstone of spacetime theory lies in the energy-matter relationship defined by Einstein's famous equation. This equation expresses the idea that energy and mass are interchangeable and that they both interact with spacetime. Massive objects curve spacetime, and this curvature, in turn, tells objects how to move. This elegant interplay governs everything from the orbit of planets to the formation of galaxies. It's an ever-present reminder that the forces shaping our universe are deeply interconnected. In the context of black holes, this equation takes on a mind-bending significance. As matter is pulled into a black hole, it is compressed into an incredibly small space. The gravitational pull becomes so strong that even light cannot escape, but the energy-matter equivalence implies that the black hole retains the energy of the objects it consumes. This leads to phenomena like Hawking radiation, a theoretical prediction by physicist Stephen Hawking. He proposed that black holes might slowly lose energy over time through quantum processes, effectively evaporating over billions of years. This concept connects quantum mechanics with spacetime and hints at a deeper, unified theory that might one day bridge these seemingly incompatible domains. Another fascinating aspect of spacetime is its apparent flexibility. Unlike the rigid Newtonian view of an absolute space and time, Einstein's spacetime is dynamic and can stretch, compress, or ripple. This flexibility is what makes phenomena like gravitational waves possible. When massive objects accelerate, such as during the collision of two black holes, they disturb spacetime, sending out ripples that propagate at the speed of light. These waves carry information about their source, allowing us to listen to events that occurred millions or even billions of years ago. The implications of gravitational waves extend beyond pure science. As our ability to detect these waves improves, we might one day use them as tools for mapping the universe. Imagine a future where gravitational wave observatories function like telescopes, revealing hidden aspects of cosmic evolution and uncovering new phenomena we cannot yet imagine. Such advancements would deepen our understanding of the universe's structure and provide new avenues for exploration. This brings us to the idea of cosmic inflation, a theory that describes the rapid expansion of spacetime in the early moments of the universe. Inflation suggests that spacetime itself expanded faster than the speed of light, stretching quantum fluctuations into the seeds of galaxies. This theory not only explains the universe's large-scale uniformity, but also hints at the possibility of a multiverse, an ensemble of universes with varying physical laws and constants. If inflation created multiple bubbles of spacetime, then our universe might be just one among countless others. This idea transforms our understanding of spacetime from a single, all-encompassing entity into a potentially infinite mosaic of interconnected realities. The multiverse hypothesis also raises profound questions about time. In some models, each universe might have its own unique timeline, with its own version of past, present, and future. Others propose that time could flow differently in different regions of the multiverse, creating scenarios where causality itself becomes fluid. While these ideas remain speculative, they challenge our most basic assumptions about spacetime and encourage us to think beyond the limits of human experience. Back in our own universe, spacetime plays a critical role in cosmology, particularly in understanding dark energy and dark matter. Dark energy is thought to drive the accelerated expansion of the universe, while dark matter provides the unseen gravitational glue that holds galaxies together. Both phenomena interact with spacetime in ways we don't yet fully understand. For instance, dark energy might be a property of spacetime itself, an intrinsic, vacuum energy, that pushes the cosmos apart. If true, it means that spacetime is not a passive stage for cosmic events but an active participant in shaping the universe's destiny. Meanwhile, dark matter warps spacetime without emitting light or other electromagnetic radiation, making it detectable only through its gravitational effects. The search for dark matter involves everything from underground detectors to particle accelerators, all aimed at uncovering what this mysterious substance is and how it interacts with spacetime. Some theories even suggest that dark matter might consist of exotic particles that exist in higher dimensions of spacetime, further blurring the line between science fiction and reality. As we probe these mysteries, one question looms large: what is the ultimate fate of spacetime? Theories about the universe's long-term future range from a big freeze, where expansion continues until all energy is evenly distributed, to a big crunch, where gravity eventually reverses the expansion, causing spacetime to collapse back into a singularity. Another possibility is the Big Rip, where dark energy becomes so dominant that it tears apart galaxies, stars, and even atoms. Each scenario paints a different picture of spacetime's endgame, yet all are grounded in our current understanding of relativity and cosmology. Even as we contemplate these distant futures, spacetime remains a key player in the here and now. For astronauts venturing into deep space, understanding spacetime is essential for planning missions, navigating through gravitational fields, and dealing with time dilation. The closer we get to achieving interstellar travel, the more critical our grasp of spacetime will become. Consider the concept of cryogenic sleep or stasis for long-duration missions. If time dilation could be harnessed effectively, astronauts traveling at near-light speeds might experience only a few years of travel, while centuries pass on Earth. This raises ethical and practical questions about what it means to leave behind the familiar flow of time for the sake of exploration. Ultimately, spacetime is more than a scientific framework. It's a testament to humanity's ability to question, imagine, and explore. It challenges us to think beyond our immediate experiences and consider the broader, often paradoxical, nature of reality. As we continue to unravel its mysteries, spacetime will undoubtedly remain at the forefront of both our scientific endeavors and our philosophical inquiries. The exploration of spacetime is an ongoing journey that merges science with philosophy, technology with imagination, and facts with speculation. One of the most fascinating aspects of spacetime lies in how it shapes our perception of the universe, and in turn, how our understanding of it shapes our actions as a species. As we dive deeper into the concepts of spacetime, time dilation, gravitational effects, and cosmic evolution, we are forced to confront questions that challenge our understanding of reality. For instance, the concept of causality, the relationship between cause and effect, takes on a new dimension when viewed through the lens of spacetime. In our everyday experiences, causality feels straightforward. An action leads to a reaction, and events unfold in a sequence dictated by time. However, relativity complicates this narrative. Under certain extreme conditions, such as near a black hole or within a wormhole, the sequence of events might appear to reverse or loop. This raises profound questions about the nature of free will, determinism, and the possibility of altering the past. Wormholes, or Einstein-Rosen bridges, serve as a thought-provoking example. These hypothetical shortcuts through spacetime could theoretically connect two distant points, allowing for faster-than-light travel. While they remain speculative, wormholes are grounded in the equations of general relativity and have captured the imagination of scientists and science fiction writers alike. If traversable wormholes were possible, they could revolutionize space travel and open up new ways of thinking about spacetime. However, wormholes come with their own set of challenges. For one, maintaining a wormhole's stability would require exotic matter with negative energy density, a concept that, while not entirely ruled out, remains beyond our current technological capabilities. Moreover, the presence of a wormhole could lead to paradoxes, such as the infamous grandfather paradox, where traveling back in time might allow someone to alter events in ways that defy logic. The interplay between time and space becomes even more intricate when we consider the potential for closed time-like curves, CTCs. These are theoretical loops in spacetime that could allow an object to return to its own past. While CTCs are mathematically plausible in certain solutions to Einstein's equations, their existence would challenge our fundamental understanding of causality and the arrow of time. The idea of time looping back on itself raises questions not just about physics, but about the very fabric of reality. On a more practical level, spacetime continues to influence the design and planning of space missions. The precise calculations required to send spacecraft to distant planets rely on our understanding of gravitational forces and the curvature of spacetime. For example, when NASA sends probes to explore the outer planets, they often use gravitational slingshots, maneuvers that involve harnessing a planet's gravity to accelerate a spacecraft. These maneuvers are a direct application of our knowledge of spacetime dynamics and allow us to reach destinations that would otherwise be out of reach. As we push the boundaries of space exploration, the role of spacetime becomes even more critical. Projects like the James Webb Space Telescope and future gravitational wave detectors aim to peer deeper into the cosmos than ever before, unraveling the history of spacetime itself. These instruments allow us to observe the universe as it was billions of years ago, providing insights into the early stages of cosmic evolution. One of the most profound questions tied to spacetime is the nature of the cosmic horizon. This is the maximum distance from which light has had time to reach us since the beginning of the universe. Beyond this horizon lies a realm we cannot observe, a reminder of the limits imposed by spacetime. The concept of the cosmic horizon forces us to grapple with the fact that our understanding of the universe is inherently incomplete, bounded by the constraints of light and time. The study of spacetime also intersects with quantum mechanics, leading to some of the most compelling and perplexing theories in modern physics. Quantum gravity, for instance, seeks to reconcile the large-scale effects of general relativity with the small-scale behaviors of quantum particles. The search for a unified theory, sometimes called the theory of everything, remains one of the greatest challenges in physics. If successful, it could provide a deeper understanding of spacetime, shedding light on phenomena like black hole singularities and the very origin of the universe. In addition to its scientific implications, spacetime invites philosophical reflections. What does it mean to exist in a universe governed by such intricate laws? How does the nature of spacetime influence our perception of time, memory, and identity? These questions remind us that spacetime is not just a scientific concept but a profound lens through which we view our place in the cosmos. As we continue to explore these mysteries, one thing becomes clear: spacetime is far more than a backdrop for cosmic events. It is an active participant in the universe's story, shaping and being shaped by the matter, energy, and forces it contains. Our journey into the depths of spacetime is a testament to human curiosity and resilience, a reminder that the universe is as much a mystery as it is a home. From the tiniest particles to the largest galaxies, from the fleeting moments of a second to the infinite stretch of eternity, spacetime encompasses it all. It challenges us to think beyond our immediate experiences, to question the boundaries of knowledge, and to imagine what lies beyond the horizon of understanding. In spacetime, we find not only the mechanics of the universe but the essence of its wonder. As we delve deeper into the intricacies of spacetime, it's worth addressing how the interplay between time and space shapes our fundamental understanding of reality. Einstein's theories of relativity didn't just redefine physics, they redefined how we think about existence itself. They challenged the Newtonian view of an absolute, unchanging clock ticking away in the background and instead introduced a universe where time and space are dynamic, malleable, and interconnected. Consider the very idea that time is not universal. Depending on where you are and how fast you're moving, time ticks at different rates. This concept, known as time dilation, is a direct result of Einstein's special relativity. If two observers are in relative motion, each perceives the other's clock as running slower. This isn't just theoretical, it's been experimentally verified, particularly through tests involving highly accurate atomic clocks placed on fast-moving aircraft or satellites. Gravitational time dilation, an extension of general relativity, takes this concept further. It tells us that the stronger the gravitational field, the slower time moves. This is why clocks on Earth's surface tick slightly slower than clocks aboard satellites orbiting the planet. Without accounting for this discrepancy, systems like GPS would be rendered inaccurate within hours. It's astonishing to think that a concept so abstract, time running at different speeds, has such tangible applications in everyday life. This bending of time and space extends to some of the most extreme environments in the universe. Near a black hole, for example, the curvature of spacetime becomes so intense that time itself nearly halts from an external observer's perspective. This phenomenon is not just a scientific curiosity. It raises profound questions about the nature of reality. If someone were to approach a black hole, they would experience time normally from their perspective, while an outside observer would see them moving increasingly slowly, eventually appearing frozen at the event horizon. Such relativistic effects aren't limited to theoretical black hole scenarios. They have profound implications for space travel. Imagine a journey to a star system several light-years away. If a spacecraft were to approach speeds close to that of light, time would slow dramatically for those aboard due to time dilation. A journey that feels like mere years to the travelers could correspond to centuries passing back on Earth. This means that, in theory, interstellar travel is possible, but it also means leaving behind a world that would age and change beyond recognition by the time of the traveler's return. The dual nature of time as both a personal experience and a cosmic constant is a recurring theme in the study of spacetime. On a human scale, time feels linear and irreversible. On a cosmic scale, however, time is far more complex. Some physicists speculate that the universe could have regions where time flows differently, or perhaps doesn't flow at all. Others suggest that time itself might be an emergent property, arising from deeper, yet to be understood principles. As we advance technologically, we continue to test and expand these theories. Gravitational wave observatories like LIGO and Virgo, which detect ripples in spacetime caused by massive cosmic events, provide direct evidence of spacetime's dynamism. These waves, generated by phenomena such as merging black holes or neutron stars, stretch and compress space itself as they travel across the universe. Observing them not only confirms Einstein's predictions but also opens a new window into the cosmos, allowing us to hear events billions of light years away. Moreover, spacetime plays a central role in theories attempting to unify the forces of nature. String theory, for example, posits that fundamental particles are not point-like but are instead tiny vibrating strings. The vibrations of these strings occur within the fabric of spacetime itself, and the theory suggests that spacetime may have additional dimensions beyond the familiar three of space and one of time. If proven, this could radically alter our understanding of the universe. Quantum mechanics adds another layer of complexity. While relativity governs the large-scale structure of spacetime, quantum mechanics deals with the subatomic world. At these tiny scales, the smooth fabric of spacetime predicted by relativity may break down, replaced by a chaotic quantum foam. Reconciling these two frameworks, relativity and quantum mechanics, is one of the greatest challenges in modern physics. A successful theory of quantum gravity could reveal what spacetime truly is at its most fundamental level. In practical terms, understanding spacetime is crucial for the future of space exploration. As we dream of sending humans to Mars, building moon bases, or even venturing to the outer planets, our ability to navigate and survive in the vastness of space depends on mastering the rules of spacetime. From calculating trajectories to managing the effects of microgravity on human bodies, every aspect of space travel is governed by the principles of spacetime. Even more ambitious are concepts like warp drives and artificial gravity, both of which hinge on manipulating spacetime itself. A warp drive, as theorized in speculative physics, would involve contracting space in front of a spacecraft and expanding it behind, effectively, surfing through spacetime faster than light without violating relativity. While such technologies remain far beyond our current capabilities, they underscore how our understanding of spacetime continues to inspire innovation and imagination. At its core, spacetime is more than a scientific framework. It is a testament to the power of human curiosity. It challenges us to think beyond our immediate experiences and to grapple with concepts that stretch the limits of comprehension. The study of spacetime doesn't just answer questions, it raises new ones, pushing us ever closer to understanding the universe and our place within it. Even as we unlock the mysteries of spacetime, we are reminded of its vastness and complexity. It is a reminder that while we have come far in our journey of discovery, there is still so much left to explore. In the interplay of time and space, we find a mirror reflecting our own quest for meaning, a journey that spans not just distances but dimensions, not just seconds but eternities. As we continue to explore the boundaries of spacetime, it's worth considering some of the deeper, more philosophical implications of these discoveries. Time and space are fundamental to our understanding of existence, but what if they are not the ultimate truths about reality? In the vastness of the cosmos, with its billions of galaxies and the mysterious nature of dark matter and dark energy, we might be missing something essential about the very fabric of the universe. One intriguing possibility that has emerged from modern physics is the idea that time, as we experience it, may not be an inherent property of the universe at all. The theory of time as an illusion, proposed by certain interpretations of quantum mechanics and cosmology, suggests that time may be a human construct, emerging from the underlying laws that govern the universe. In this view, time itself could be emergent, appearing only under certain conditions and in specific systems. This challenges our very conception of time as a continuous and linear flow. If time is an illusion, then what does that mean for the events that shape our lives? Can we truly say that the past is gone, the future is yet to come, and the present is a fleeting moment? Some researchers have even proposed that the concept of The arrow of time, the one-directional flow of time from past to future, might only be an artifact of our perceptions, shaped by thermodynamics and entropy. This raises the possibility that the universe itself, at its most fundamental level, might not adhere to the same constraints we impose on it. On the other hand, the idea of time as an illusion is not universally accepted, and many physicists continue to embrace the concept of time as an integral part of the universe. For example, in general relativity, time and space are intertwined in a way that gives them both a very real and measurable effect on the world around us. Time dilation and gravitational time shifts are not abstract concepts. They are real effects that can be observed and measured. They shape the way we live and travel, and they will continue to influence the future of space exploration. Understanding the true nature of time and space is crucial for advancing our capabilities in space exploration. Our current technological limitations are, in many ways, a result of our inability to fully grasp the implications of relativity. The very concept of interstellar travel hinges on understanding how time behaves at extreme velocities or in the presence of intense gravitational fields. The success or failure of missions to distant stars will depend not just on how we build spacecraft, but on how we understand the interplay of time and space as we traverse the vast distances between us and the cosmos. Take, for example, the challenge of traveling to Proxima Centauri, the closest star to our solar system. The journey would take thousands of years using current spacecraft technology. However, by exploiting the principles of relativistic time dilation, it's theoretically possible to significantly shorten the duration of the trip for the travelers aboard. If a spacecraft could travel at near light speed, the passage of time would slow down for the crew, while centuries or even millennia would pass for those remaining on Earth. This presents a fascinating paradox. The astronauts would experience only a fraction of the journey's time, but the generations left behind on Earth would witness the slow passage of centuries as the spacecraft continues its journey. While this sounds like science fiction, the mathematics of special and general relativity suggests that such time dilation effects are indeed possible. In the near future, we may witness missions that, though they might take decades or centuries in human time, are only a brief instant relative to the travelers on board. As we continue to push the boundaries of space exploration, we will have to come to terms with the reality of time as a malleable, flexible concept. However, the relationship between space and time isn't solely a theoretical concept. Its effects are visible in our everyday lives, albeit in small, nearly imperceptible ways. The GPS systems that guide us through our daily commutes are a perfect example of this. The satellites that orbit Earth operate in a different gravitational field than we do on the surface. As a result, time moves slightly faster for these satellites than it does for us on Earth. Without adjusting for this difference in time, our GPS devices would become inaccurate within a matter of hours, leading to errors in navigation that could have serious consequences. This is just one example of how our modern understanding of spacetime has practical, real-world applications. As we continue to refine our understanding of spacetime, these effects will only become more apparent, influencing everything from communication systems to the design of future spacecraft. The ability to measure and account for time dilation and other relativistic effects will be critical for the success of long-duration space missions, and will guide the development of technologies that could one day allow us to travel across the stars. The implications of relativity also extend to our understanding of the universe's structure itself. One of the most profound consequences of general relativity is the prediction of the existence of black holes, regions of spacetime where gravity is so intense that nothing, not even light, can escape. These objects have captured the imaginations of scientists and the public alike, not only because of their strange and enigmatic nature but because they challenge our understanding of space, time, and the fundamental laws of physics. The study of black holes has revealed fascinating insights into the nature of spacetime. At the heart of a black hole lies a singularity, an infinitely dense point where spacetime itself breaks down, and the laws of physics, as we know them, cease to function. Here, both time and space are stretched to their limits, and the normal rules that govern our universe no longer apply. Understanding what happens at the singularity is one of the greatest unsolved mysteries in modern physics. For centuries, black holes were considered purely theoretical objects, but in recent years, we've gathered direct evidence of their existence. The first photograph of a black hole, taken by the Event Horizon Telescope in 2019, provided a stunning visual confirmation of these cosmic behemoths. The black hole in question, located in the galaxy M87, is 6.5 billion times the mass of the Sun and resides at the center of the galaxy, where its gravitational influence dominates the surrounding space. The study of black holes has profound implications for our understanding of time. As objects approach the event horizon of a black hole, time itself begins to warp. From an outside observer's perspective, anything falling into the black hole seems to slow down and eventually freeze as it nears the event horizon. To the person or object falling in, however, time continues at its normal pace. This creates a paradox. While time seems to stand still for an outside observer, it flows normally for the object or person inside the event horizon. This concept of time dilation at the event horizon is one of the most fascinating and puzzling aspects of black holes. It raises questions about the nature of time itself and challenges our conventional understanding of cause and effect. If time can slow down to the point where it seems to stop, what does this mean for our perception of reality? Does the fabric of spacetime break down at the event horizon, and if so, what happens to the information that falls into the black hole? These questions are at the forefront of theoretical physics and cosmology, and they may hold the key to unlocking some of the universe's most profound mysteries. As we delve deeper into the mysteries of black holes and their connection to time, we find that the relationship between space and time is far more intricate than we ever imagined. Black holes, with their extreme gravitational fields, offer a glimpse into the very heart of spacetime itself. But beyond black holes, there are even more fascinating phenomena that reveal how deeply space and time are intertwined. One such phenomenon is gravitational waves. These ripples in spacetime, first predicted by Einstein in 1915, were directly detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO. Gravitational waves are created by some of the most violent and energetic processes in the universe, such as the collision of black holes or neutron stars. When these massive objects merge, they release an enormous amount of energy in the form of ripples that travel outward, distorting the fabric of spacetime itself as they go. Gravitational waves provide an entirely new way to observe the universe. Instead of relying on light, which can be blocked by dust or absorbed by cosmic objects, gravitational waves pass through matter without much interference, allowing us to observe cosmic events that would otherwise be invisible. The detection of these waves confirmed yet another key aspect of Einstein's general theory of relativity, that massive objects can create distortions in spacetime that propagate outward like ripples on a pond. This discovery has profound implications not just for our understanding of the universe, but for how we think about time and space. Gravitational waves are an example of how spacetime itself is not a static, fixed entity. Instead, it is a dynamic and malleable fabric, constantly being stretched and compressed by the movements of mass and energy. This malleability challenges our everyday experiences of space and time, where they seem fixed and unchanging, but on a cosmic scale, space and time are constantly in flux. The detection of gravitational waves also raises new questions about the nature of space and time. For example, if spacetime can be distorted by massive objects, what happens when multiple distortions collide or interact? Could there be points in the universe where spacetime itself is torn or fragmented? These questions bring us to another cutting-edge concept in modern physics, the possibility of a multiverse. The multiverse theory suggests that our universe is just one of many that exist in a vast, infinite cosmic landscape. Each of these universes might have its own set of physical laws, and some might even have entirely different dimensions of space and time. In some versions of the multiverse theory, the different universes could interact with one another, causing fluctuations in spacetime that could affect the structure of our own universe. If this is true, it would mean that time and space are not only fluid in our own universe but may also be part of a much larger, interconnected system of universes. But before we get too carried away with the idea of the multiverse, let's consider another aspect of space and time that could be just as mind-bending: wormholes. Wormholes are theoretical shortcuts through spacetime, allowing for instantaneous travel between distant points in the universe. In theory, a wormhole could connect two distant regions of space, bending time and space in such a way that a traveler could move between them almost instantaneously, bypassing the vast distances between them. The concept of wormholes is closely related to the idea of spacetime being malleable. If spacetime can be curved by massive objects, could it also be folded or compressed in such a way that distant points in space become connected by a tunnel-like structure? This is the basic idea behind a wormhole, a bridge between two distant points in spacetime. However, wormholes are not just theoretical curiosities. They could, in principle, provide a means of faster-than-light travel, revolutionizing space exploration and making interstellar journeys a reality. The idea of wormholes is intriguing, but there are many unanswered questions about whether they can exist in reality. For one, wormholes would require an immense amount of energy to stabilize, and it's unclear if we have the technology or understanding to create such conditions. Moreover, even if wormholes could exist, they might not be stable enough for human travel. Theoretical physicists are still working on understanding the conditions under which a wormhole could form, and whether it's possible for anything, let alone a human traveler, to safely pass through one. Even if wormholes remain a theoretical concept, they serve as a reminder of how deeply intertwined space and time are. The very idea of a shortcut through space-time challenges our traditional notions of how we travel through the universe. If space-time is flexible and malleable, then the way we think about distance, time, and movement must be re-examined. What would it mean for our understanding of time if we could travel vast distances in an instant? Would time still flow the same way for a traveler moving through a wormhole, or would they experience time differently than those who remain outside the wormhole? These questions blur the lines between science fiction and scientific possibility, pushing us to rethink the nature of reality itself. While we've explored some of the most mind-bending consequences of relativity, there are still many mysteries waiting to be unraveled. One of the most intriguing areas of research is the study of dark matter and dark energy. These two invisible forces make up about 95% of the universe, yet we have little understanding of what they are or how they interact with the rest of the cosmos. Dark matter, which accounts for about 27% of the universe's mass, is believed to be responsible for the way galaxies behave. Without dark matter, galaxies would not have enough gravitational pull to hold themselves together. Yet, despite its gravitational effects, dark matter doesn't interact with light or other forms of electromagnetic radiation, making it invisible and detectable only through its gravitational influence. Dark energy, on the other hand, is a mysterious force that is driving the accelerated expansion of the universe. While we know that dark energy exists, we have no idea what it is or how it works. Some theories suggest that dark energy is a form of vacuum energy, a fundamental property of space itself that causes the expansion of the universe to accelerate. Others speculate that dark energy could be related to the structure of spacetime itself, with ripples or fluctuations in the fabric of spacetime giving rise to this mysterious force. The relationship between dark matter, dark energy, and the fabric of spacetime is one of the greatest puzzles in modern cosmology. Some scientists believe that understanding the nature of these elusive forces could help us unlock the deepest secrets of the universe, including the true nature of time and space. Could dark matter and dark energy be linked to the fundamental properties of spacetime in ways we can't yet comprehend? If so, it could offer new insights into how time and space are interwoven, and how we might one day manipulate them to explore the farthest reaches of the cosmos. As we continue to push the boundaries of our understanding of spacetime, we're likely to encounter even more mysteries that challenge our conception of time, space, and reality. Our journey through the cosmos has just begun, and the more we learn, the more we realize how little we truly know. Time and space, as defined by Einstein's theory of relativity, are powerful tools for understanding the universe, but they are also just the beginning of a much larger journey. What lies beyond the horizon of our current understanding? What discoveries are waiting to be made in the vast, uncharted territories of space and time? As we look to the future of space exploration, one thing is certain: the mysteries of time and space will continue to captivate and challenge us, pushing the limits of our knowledge and imagination as we strive to unravel the deepest secrets of the universe. Our journey into the mysteries of time and space wouldn't be complete without discussing the fascinating concept of time travel. Few ideas captivate the imagination like the ability to move through time, whether it's to revisit the past or glimpse into the future. While time travel is often relegated to the realm of science fiction, the laws of physics, particularly Einstein's theory of relativity, suggest that it might be theoretically possible under certain conditions. Einstein's equations reveal that time is not an absolute constant, it is relative, and depends on the observer's speed and gravitational environment. This opens the door to scenarios where time travel could occur. For instance, if an object or a person were to travel at speeds close to the speed of light, they would experience time much more slowly than someone who remained stationary. This effect, known as time dilation, means that an astronaut traveling at near-light speeds could return to Earth having aged only a few years, while decades or even centuries might have passed for those who stayed behind. This is a form of forward time travel that is firmly rooted in the principles of relativity. But what about traveling to the past? This idea is much more controversial and fraught with paradoxes. One of the most well-known is the grandfather paradox, which questions what would happen if a time traveler went back and altered the past in a way that prevents their own existence. For example, if someone traveled back in time and prevented their grandparents from meeting, would they cease to exist? And if so, how could they have traveled back in the first place? These logical conundrums make backward time travel a contentious topic, even among theoretical physicists. However, certain solutions in Einstein's equations suggest that backward time travel might not be entirely impossible. One such solution involves closed time-like curves, CTCs, which are loops in spacetime that could theoretically allow an object to return to its own past. CTCs have been studied in the context of wormholes, which we discussed earlier. If a wormhole could be manipulated to connect 2 points in time rather than 2 points in space, it could create a pathway for traveling into the past. Yet, this idea remains speculative, as it would require conditions, such as negative energy or exotic matter, that are not yet understood or achievable. Another intriguing concept related to time travel is the idea of cosmic strings. These are hypothetical, incredibly thin and dense structures thought to have formed during the early universe. If two cosmic strings were to pass close to one another at near-light speeds, they could create a space-time configuration that allows for time travel. However, like wormholes, the existence of cosmic strings is purely theoretical, and their practical application to time travel is far from being realized. While the mechanics of time travel remain speculative, its implications are profound. If time travel were possible, it could fundamentally alter our understanding of causality, the relationship between cause and effect. In a universe where the future could influence the past, the very fabric of reality would need to be redefined. This has led some scientists to propose that certain cosmic censorship principles might prevent time travel to the past to avoid such paradoxes. But time travel isn't just a theoretical exercise. It has practical implications for our exploration of the universe. For example, time dilation is already a consideration in long-term space missions. Astronauts on high-speed missions to distant planets or stars would experience time differently than those on Earth, creating what's sometimes called the twin paradox. In this scenario, an astronaut traveling at relativistic speeds could return to find that their twin, who stayed on Earth, has aged much more than they have. Understanding and accounting for these effects is crucial as we plan for interstellar exploration. Time travel also raises philosophical questions about the nature of time itself. Is time a linear progression from past to future, or is it more like a landscape where all moments exist simultaneously, waiting to be accessed? Some interpretations of quantum mechanics, such as the many worlds interpretation, suggest that every possible outcome of every event creates a new, parallel universe. If this is true, then time travel might not involve altering our own timeline but rather branching off into a new one. The idea of parallel universes brings us back to the multiverse, a concept we touched on earlier. If our universe is just one of many, each with its own unique timeline, then time travel could involve moving between these timelines rather than within a single one. This would eliminate the paradoxes associated with altering the past, as any changes made in a parallel timeline wouldn't affect the original one. Whether or not time travel ever becomes a reality, the study of time and its relationship to space continues to push the boundaries of science and philosophy. It forces us to confront fundamental questions about the nature of reality, the limits of human knowledge, and our place in the universe. As we explore these questions, we are reminded that our understanding of time and space is still in its infancy. The universe is vast and mysterious, and each new discovery opens up more questions than answers. The relationship between time and space is not just a scientific curiosity. It is a profound mystery that touches on the deepest aspects of existence. From the bending of spacetime around black holes to the ripples of gravitational waves, from the possibility of wormholes to the tantalizing idea of time travel, each new insight brings us closer to understanding the true nature of the cosmos. Yet, with each answer, we are reminded of how much we still have to learn. As we stand on the brink of new discoveries, one thing is clear: the mysteries of time and space will continue to inspire and challenge us for generations to come. They are not just abstract concepts for scientists and philosophers to ponder. They are the very fabric of our reality, shaping the universe we inhabit and the lives we lead. In the dance of time and space, we are but fleeting moments, yet our curiosity and desire to understand may one day unlock the secrets of the cosmos itself. The journey into the relationship between time and space also requires us to explore the concept of the arrow of time. This refers to the seemingly one-way direction in which time flows, from the past, through the present, and into the future. But what dictates this direction, and could it ever be reversed? To answer these questions, we must delve into the realms of thermodynamics, quantum mechanics, and cosmology. One of the key explanations for the arrow of time lies in the second law of thermodynamics. This law states that the total entropy, or disorder, of a closed system will always increase over time. In simple terms, things tend to move from order to chaos. Imagine breaking a glass. It shatters into countless pieces, becoming more disordered. But the reverse process, those pieces spontaneously reassembling into a glass, never happens. This increase in entropy gives time its direction and helps explain why we remember the past but not the future. Entropy doesn't just govern the flow of time in everyday life, it also plays a crucial role on a cosmic scale. At the beginning of the universe, during the Big Bang, entropy was at an extraordinarily low level. As the universe expanded and evolved, entropy increased, driving the arrow of time forward. But what happens if the universe stops expanding and begins to contract? Could the arrow of time reverse? While this is a subject of debate, some theories suggest that time might flow backward in a contracting universe, though this idea challenges our current understanding of physics. Quantum mechanics adds another layer of complexity to our understanding of time. On the quantum scale, particles don't follow the deterministic paths we see in everyday objects. Instead, they exist in a state of probabilities until they are observed. This raises intriguing questions about the nature of time. Is it continuous and flowing, or is it discrete, consisting of individual moments, strung together like frames in a film? Some physicists argue that time might not be fundamental at all but rather an emergent property of the universe, arising from deeper, underlying laws. The concept of time as an emergent property is closely tied to theories of quantum gravity, which aim to reconcile general relativity with quantum mechanics. In these theories, spacetime itself might be a kind of illusion that emerges from the interactions of quantum particles or strings. If this is true, our everyday experience of time could be just one perspective on a much more complex reality. The relationship between time and gravity also challenges our intuitions. As we've discussed, massive objects like stars and black holes warp spacetime, creating gravitational time dilation. But gravity doesn't just slow down time, it also affects how we perceive the passage of time. For example, experiments have shown that people living at higher altitudes, where gravity is slightly weaker, age faster than those at sea level. These differences are minuscule but measurable, and they highlight the intimate connection between time and the physical environment. The effects of gravity on time become even more extreme near black holes, where space-time is warped to its limits. If you were to approach the event horizon of a black hole, time would slow down dramatically for you relative to an outside observer. To someone watching from a safe distance, it would appear as if you were frozen in time, never actually crossing the event horizon. Meanwhile, from your perspective, time would continue as usual, but you would see the outside universe speeding up, potentially witnessing the entire future of the cosmos in what feels like moments. This extreme time dilation near black holes has fascinating implications for space exploration. Imagine using the intense gravitational field of a black hole as a kind of time machine to travel into the far future. While the practicalities of such a journey are beyond our current capabilities, the idea underscores the incredible interplay between time, space, and gravity. Another intriguing aspect of time and space is the concept of spacetime. Foam. At the smallest scales, quantum theory suggests that spacetime might not be smooth and continuous but rather a frothy, turbulent sea of fluctuations. This spacetime foam could have profound implications for our understanding of time. For instance, it might allow for tiny, fleeting connections between different points in time and space, miniature wormholes that appear and disappear in an instant. While these quantum effects are far too small to observe directly, they could hold the key to understanding the true nature of time. As we continue to explore these mysteries, it's important to remember that our understanding of time and space is still evolving. The more we learn, the more we realize how much we don't know. Each discovery opens up new questions, challenging us to think in ways that defy our everyday experiences and intuitions. The relationship between time and space isn't just a topic for theoretical physicists. It has practical implications for our future. As we venture further into the cosmos, understanding the effects of relativity, time dilation, and gravitational time shifts will be crucial for planning long-term missions. Whether it's sending astronauts to Mars, exploring the outer reaches of the solar system, or even journeying to other stars, the interplay between time and space will shape every aspect of our exploration. At the same time, the study of time and space touches on some of the most profound philosophical questions we can ask. What is time? Is it a fundamental aspect of reality, or is it something we impose on the universe to make sense of it? Does the future already exist, waiting to be discovered, or is it created moment by moment as time unfolds? These questions remind us that science and philosophy are deeply interconnected, each enriching the other as we seek to understand the universe and our place within it. Ultimately, the mysteries of time and space are a testament to the boundless curiosity and creativity of the human mind. They challenge us to think beyond our everyday experiences, to question what we take for granted, and to imagine possibilities that stretch the limits of our imagination. As we continue to explore these mysteries, one thing is certain: the relationship between time and space will remain one of the most fascinating and enduring questions of our time. Exploring the vast relationship between time and space also forces us to grapple with the idea of causality, the principle that every effect has a cause. Causality underpins much of our understanding of how the universe operates, yet relativity introduces scenarios where causality seems to blur. When you introduce concepts like time dilation or the potential for faster-than-light travel through hypothetical constructs like wormholes, you encounter situations where the cause could seemingly occur after the effect, flipping the natural order of events. This paradox challenges not only physics but also our fundamental grasp of reality. Let's take the example of hypothetical faster-than-light communication or travel. According to Einstein's special relativity, as an object approaches the speed of light, time slows down relative to an outside observer. If it were possible to surpass the speed of light, the sequence of events could become jumbled depending on the observer's frame of reference. In some scenarios, this could theoretically allow information or matter to travel backward in time, violating causality and creating paradoxes. One of the most famous causality dilemmas is the grandfather paradox. Suppose someone were to travel back in time and prevent their grandparents from meeting. This would prevent the time traveler from being born, making it impossible for them to go back in time to interfere in the first place. Such paradoxes highlight the deep and unresolved questions surrounding the nature of time and causality. However, some theories attempt to resolve these paradoxes. For instance, the concept of closed time-like curves. CTCs, permitted in certain solutions to Einstein's equations, suggests that time travel could occur in a way that preserves consistency. In a universe with CTCs, any action taken by a time traveler would already be part of history, ensuring that causality is not violated. This idea, while speculative, opens up fascinating possibilities for how time might work on a fundamental level. Another resolution to time travel paradoxes comes from the many worlds interpretation of quantum mechanics. According to this interpretation, every quantum event creates a branching of the universe into different timelines. In this framework, traveling back in time would not alter the traveler's original timeline but instead create a new, parallel timeline. While this avoids paradoxes, it raises new questions about the nature of reality and the existence of multiple universes. Speaking of parallel universes, the multiverse hypothesis offers yet another perspective on time and space. If there are countless universes, each with its own version of spacetime, then time as we experience it might be just one of many possible configurations. In some universes, time might flow backward or in loops, or it might not exist at all in any recognizable form. While the multiverse remains a speculative concept, it pushes us to think about time and space in ways that go far beyond our everyday experiences. The nature of spacetime itself becomes even more enigmatic when we consider the quantum realm. On the smallest scales, spacetime appears to be far from the smooth fabric described by general relativity. Instead, it is thought to be quantized, made up of tiny, discrete units. This idea is central to the search for a theory of quantum gravity, which seeks to unify general relativity with quantum mechanics. One promising approach to quantum gravity is string theory, which posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings of energy. In string theory, spacetime is a dynamic entity that emerges from the interactions of these strings. This means that time and space are not fixed backdrops against which events unfold but are instead shaped by the very processes they contain. Another approach is loop quantum gravity, which envisions spacetime as a network of interconnected loops. In this framework, time and space are not continuous but are composed of discrete chunks. This granular structure of spacetime could help explain some of the strange phenomena observed at the quantum level and might even shed light on the origins of the universe itself. These cutting-edge theories are not just academic exercises. They have profound implications for our understanding of reality. If spacetime is quantized, it could mean that time itself has a smallest possible unit, a quantum of time. This would fundamentally change how we think about the flow of time, and could open the door to new technologies and ways of exploring the universe. The implications of these theories extend to the concept of the universe's beginning and end. The Big Bang theory describes the universe's origin as a singularity, a point of infinite density where spacetime itself breaks down. But what happened before the Big Bang? And what will happen in the distant future, as the universe continues to expand? These questions challenge our understanding of time and space at the most fundamental level. Some theories suggest that the universe might go through cycles of expansion and contraction, with each cycle representing a new Big Bang and Big Crunch. In such a model, time as we know it might reset with each cycle, creating an endless loop of cosmic rebirth. Other theories propose that the universe will continue expanding forever, eventually reaching a state of maximum entropy where all processes cease, a scenario sometimes called the heat death of the universe. The exploration of time and space isn't just about understanding the universe on the grandest scales. It also has profound implications for our own existence. As humans, we experience time in a deeply personal way, marked by memories of the past and hopes for the future. But what if our perception of time is just an illusion? Some philosophers and physicists argue that the past, present, and future all coexist in a block universe, where time is simply another dimension, like space. In this view, the flow of time is a construct of human consciousness, not a fundamental feature of reality. These ideas are more than just intellectual curiosities. They challenge us to rethink our place in the cosmos. If time is an illusion or an emergent property, what does that mean for concepts like free will, identity, and the meaning of life? The study of time and space forces us to confront these profound questions, pushing the boundaries of science, philosophy, and human imagination. As we continue to explore the relationship between time and space, we are reminded of the immense complexity and beauty of the universe. Each discovery brings us closer to understanding the fundamental nature of reality, yet it also reveals new mysteries that beckon us to keep exploring. The journey is far from over, and the possibilities are as boundless as time and space themselves. Building upon the profound relationship between time and space, we must delve further into how these concepts intertwine with human exploration and understanding. The idea that time and space are not static but dynamic and interdependent forces reshapes not just theoretical physics but also practical applications like space exploration, global communication, and the quest to comprehend our place in the universe. For instance, the concept of time dilation has practical implications for astronauts traveling through space at high velocities. According to special relativity, as you approach the speed of light, time slows down relative to an observer at rest. Imagine an astronaut on a spacecraft traveling near light speed. To the astronaut, the journey might feel like a few years, but for those left on Earth, decades could pass. This phenomenon, often referred to as the twin paradox, is more than a theoretical curiosity. It's a real effect measured in experiments and in the behavior of particles traveling at near light speeds. Time dilation also plays a critical role in the functionality of GPS satellites orbiting Earth. These satellites rely on highly accurate atomic clocks to provide location data. However, because they are moving at high speeds relative to the surface of the Earth and are further from the planet's gravitational pull, the passage of time for these clocks differs from that on the ground. Engineers must account for both special and general relativistic effects to ensure the system's accuracy. Without these adjustments, the GPS system would drift by several kilometers each day, rendering it useless for navigation. This brings us to another fascinating phenomenon: gravitational time dilation. According to general relativity, time passes more slowly in stronger gravitational fields. This effect has been measured in experiments and even observed on Earth, where clocks at sea level tick slightly slower than those at higher altitudes. In the grander scheme, gravitational time dilation influences our understanding of black holes, those enigmatic regions of spacetime where gravity is so intense that nothing, not even light, can escape. Black holes provide a natural laboratory for studying the extremes of spacetime. Near the event horizon, the boundary beyond which nothing can return, the warping of spacetime becomes so severe that time slows dramatically. To a distant observer, objects falling toward a black hole appear to slow down and freeze as they approach the event horizon, a visual manifestation of time dilation. For the object itself, time would seem to proceed normally, but the gravitational forces would stretch and distort it beyond recognition. These phenomena raise intriguing questions about the nature of reality. If time can stretch and contract depending on the circumstances, what does that say about its true nature? Is time a universal constant, or is it inherently tied to the observer's frame of reference? These questions remain at the forefront of physics, driving new theories and experiments aimed at uncovering the deeper truths of the cosmos. One area of active research is the study of wormholes, theoretical shortcuts through spacetime that could connect distant parts of the universe. If wormholes exist, they might allow for faster-than-light travel or even time travel. However, their existence remains speculative, and their stability is a significant challenge. Current theories suggest that wormholes would collapse almost immediately after forming unless they were held open by an exotic form of matter with negative energy density, a concept that itself remains theoretical. Even if wormholes prove to be purely theoretical constructs, their study expands our understanding of spacetime's possibilities. They serve as a reminder that our current understanding is far from complete, and that the universe may hold surprises beyond our wildest imaginations. The quest to understand time and space is as much about exploring the unknown as it is about refining the known. As we continue to push the boundaries of space exploration, the interplay of time and space becomes ever more critical. Missions to other planets, moons, and eventually stars will require precise calculations that account for relativistic effects. For instance, if humanity ever embarks on a journey to a star system like Proxima Centauri, the nearest to our own at 4.24 light-years away, the travelers would experience time differently from those left on Earth. The relativistic effects would not only influence the logistics of the journey but also the psychology of the astronauts and the society awaiting their return. The psychological impact of time dilation adds another layer of complexity. Imagine leaving Earth on a mission where only a few years pass for you, but decades or even centuries pass for everyone else. By the time you return, the world would be unrecognizable, and everyone you knew might be long gone. This disconnect between personal time and universal time challenges our understanding of identity, continuity, and what it means to be human. Furthermore, the study of time and space has profound implications for our understanding of the universe's ultimate fate. Cosmologists debate whether the universe will continue expanding forever, slow, and eventually reverse into a big crunch, or reach a state of equilibrium in a big freeze. Each scenario is tied to the nature of spacetime and the interplay of gravity, dark energy, and the universe's overall geometry. Dark energy, a mysterious force driving the accelerated expansion of the universe, adds another layer of intrigue. If dark energy continues to dominate, the fabric of spacetime could stretch to the point where galaxies, stars, and eventually atoms are torn apart, a scenario known as the Big Rip. Understanding dark energy is one of the greatest challenges in modern physics, and could hold the key to understanding the true nature of time and space. Even on smaller scales, the quantum nature of spacetime presents challenges and opportunities. In the quantum realm, the smooth fabric of spacetime envisioned by general relativity gives way to a chaotic, probabilistic landscape. This quantum foam could hold the answers to long-standing questions about the unification of quantum mechanics and general relativity, a goal often referred to as the search for a theory of everything. At its core, the study of time and space is a journey of discovery that combines the theoretical with the practical, the philosophical with the scientific. It challenges our perceptions, pushes the boundaries of what we know, and invites us to imagine what lies beyond. Whether we are exploring the depths of black holes, the far reaches of the cosmos, or the tiniest quantum fluctuations, the relationship between time and space remains one of the most compelling mysteries of existence. And as we continue to unravel these mysteries, we are reminded that our place in the universe is both insignificant and extraordinary. We are small, fleeting creatures in a vast, eternal cosmos, yet we possess the curiosity and intellect to ask the biggest questions and seek the deepest truths. The interplay of time and space is not just a scientific puzzle, it is a testament to the boundless potential of the human spirit. As we delve even deeper into the intertwined nature of time and space, the role of human ingenuity and perseverance becomes a focal point. Our exploration of these concepts not only stretches the limits of theoretical physics, but also transforms our understanding of existence, perception, and reality itself. The study of time and space isn't merely an academic endeavor, it is a profound inquiry into what it means to exist in a universe governed by such enigmatic forces. Take, for example, the idea of spacetime as a fabric. This metaphor, though simplified, helps us visualize how massive objects like planets and stars warp spacetime, much like a heavy ball placed on a stretched sheet distorts its surface. This warping creates what we perceive as gravity. Einstein's general theory of relativity redefined our understanding of gravity not as a force in the Newtonian sense, but as the curvature of spacetime caused by mass and energy. This new perspective had profound implications for both cosmology and astrophysics. Consider the bending of light by gravity, a phenomenon known as gravitational lensing. When light passes near a massive object, its path bends due to the curvature of spacetime. This effect, predicted by Einstein and later confirmed through observations, allows astronomers to study distant galaxies and even detect invisible objects like black holes and dark matter. In essence, the warping of spacetime becomes a lens through which we can view the universe. But spacetime's malleability also opens the door to even more mind-bending phenomena. One such concept is the possibility of closed time-like curves, paths through spacetime that loop back on themselves, theoretically allowing for time travel. While this idea remains speculative and fraught with paradoxes, it illustrates the profound flexibility of spacetime as described by relativity. If such loops exist, they could provide a gateway to understanding time not as a linear sequence but as a dynamic, interconnected dimension. This interconnectedness brings us to the concept of simultaneity, or, more accurately, the lack thereof. In relativistic terms, the notion that two events can occur at the same time is not absolute but depends on the observer's frame of reference. This relativistic effect was famously illustrated in Einstein's thought experiment involving a moving train. For an observer on the train, two lightning strikes at either end of the train might appear simultaneous, but for someone standing on the platform, they would seem to occur at different times. This relativity of simultaneity challenges our intuitive understanding of time as a universal constant and underscores its dependence on spatial and temporal context. The implications of this relativity are far-reaching, particularly in the realm of space exploration. As we aim to send humans further into the cosmos, the relativistic effects of time and space will become increasingly relevant. For example, long-duration missions to distant planets or moons will require precise calculations to account for the varying passage of time due to both velocity and gravitational influences. These missions will also force us to confront the psychological and social consequences of relativistic time, such as the potential for significant time discrepancies between astronauts and their counterparts on Earth. Moreover, the practical applications of relativity extend beyond space exploration into the technologies we use every day. The synchronization of clocks and global communication networks, for instance, depends on understanding and accounting for relativistic effects. Whether it's coordinating financial transactions, enabling real-time video calls, or managing data transfer across continents, our modern world is deeply reliant on the principles of relativity. This interconnectedness serves as a reminder that time and space are not abstract concepts confined to physics labs, but are integral to the fabric of contemporary life. The interplay of time and space also plays a central role in our quest to understand the universe's origins and destiny. The Big Bang Theory, which describes the universe's expansion from an initial singularity, relies on the framework of spacetime to explain how energy and matter evolved over billions of years. In this context, time itself becomes a dimension that began with the Big Bang, challenging our understanding of causality and existence. If time had a beginning, what existed before it? And if spacetime is expanding, what lies beyond its boundaries? These questions push the limits of human comprehension, but they also inspire innovative theories. One such theory is the concept of a multiverse, a collection of multiple, possibly infinite, universes with their own distinct space-time structures. In some versions of the multiverse theory, each universe could have different physical laws, leading to variations in how time and space operate. While evidence for the multiverse remains speculative, the idea broadens our perspective and underscores the vast potential of spacetime as a dynamic, multifaceted entity. Returning to the practical, the study of spacetime has revolutionized our approach to navigation and mapping. Satellite technologies like GPS rely on an intricate understanding of both the curvature of spacetime and the relativistic effects on time. By precisely measuring the differences in time experienced by satellites in orbit and receivers on Earth's surface, we can pinpoint locations with incredible accuracy. This ability has transformed industries ranging from transportation to agriculture, highlighting the tangible benefits of exploring abstract concepts like relativity. As we continue to unravel the mysteries of time and space, new technologies and theories will undoubtedly emerge, pushing the boundaries of what we know. Quantum mechanics, for instance, introduces additional complexities to our understanding of spacetime. At the quantum level, particles don't follow the deterministic paths predicted by classical physics, but instead exist in probabilistic states governed by the rules of quantum theory. Reconciling these quantum behaviors with the smooth, continuous nature of spacetime described by relativity is one of the greatest challenges in modern physics. This challenge has given rise to attempts to develop a unified theory of quantum gravity, which would bridge the gap between quantum mechanics and general relativity. Concepts like string theory and loop quantum gravity offer potential pathways, suggesting that spacetime itself might be composed of discrete, quantized units. If true, this would revolutionize our understanding of the universe, revealing a deeper, more fundamental layer of reality. In many ways, our exploration of time and space is a journey of self-discovery. By probing the nature of spacetime, we learn not just about the cosmos but also about ourselves, our perceptions, our limitations, and our capacity for innovation. The relationship between time and space is not just a scientific puzzle, it is a mirror reflecting the boundless potential of human curiosity. This profound relationship between time and space, defined by relativity, reminds us that the universe is far more interconnected and complex than our senses initially suggest. At its core, spacetime is a fabric woven with the threads of mass, energy, and motion. The very forces and dynamics that govern the stars, galaxies, and black holes are intimately linked to the same principles that influence the devices in our pockets, our global positioning systems, and even our understanding of our place in the cosmos. Consider the phenomenon of time dilation in more detail. For astronauts traveling at relativistic speeds, fractions of the speed of light, time moves slower relative to those who remain stationary on Earth. This effect, confirmed by experiments using atomic clocks on high-speed jets and satellites, illustrates the malleability of time. In theoretical scenarios, if a spaceship were to travel close to the speed of light for what felt like a few years to its occupants, they might return to an Earth where decades, even centuries, had passed. This concept, while rooted in relativity, touches on deeply human concerns about isolation, change, and the passage of time. Gravitational time dilation, another critical aspect of relativity, further demonstrates the elasticity of time. Near massive objects, such as black holes or neutron stars, the intense gravitational pull stretches and warps spacetime. Time itself slows down relative to observers in regions of weaker gravity. This phenomenon, famously depicted in movies and explored in scientific literature, isn't just a thought experiment, it has real-world implications. For instance, the clocks aboard GPS satellites tick slightly faster than those on Earth due to their altitude and weaker exposure to Earth's gravity. Engineers must account for these minuscule differences to ensure GPS accuracy, underscoring how deeply intertwined relativity is with modern technology. These principles also challenge us to think about the limits of exploration. Imagine sending probes or even crewed missions to the edge of a black hole's event horizon, where spacetime is stretched to its breaking point. Here, gravitational time dilation would be so extreme that minutes for the explorers could equate to years or centuries for those observing from a distance. This raises intriguing questions about communication, scientific observation, and even the psychological impacts of such missions. Would the explorers effectively travel into the future from the perspective of Earth? Could they return with data or experiences that redefine our understanding of the universe? Another fascinating aspect of spacetime lies in its role in defining the structure of the cosmos. Einstein's equations describe how spacetime curves in response to mass and energy, shaping the universe on the grandest scales. This curvature governs the motion of galaxies, the formation of cosmic structures, and even the expansion of the universe itself. Observations of distant galaxies reveal that the fabric of spacetime is not static but dynamic, stretching outward in all directions. This expansion, driven by dark energy, accelerates over time, suggesting that the universe's ultimate fate might involve continued growth into an ever colder, emptier void. But what about the origins of spacetime? The Big Bang Theory posits that time and space themselves emerged from an initial singularity, a point of infinite density and temperature. In this early universe, spacetime was not yet differentiated in the way we experience it today. Instead, it existed in a state of quantum flux, governed by laws that remain only partially understood. As the universe expanded and cooled, spacetime unfolded, allowing for the formation of matter, energy, and the complex structures we observe now. Yet this raises profound questions. If spacetime had a beginning, does it also have an end? Could the universe collapse back into a singularity, reversing the Big Bang in a process known as the Big Crunch? Or could spacetime tear apart under the influence of dark energy, resulting in a Big Rip? These scenarios, while speculative, highlight the mysterious and dynamic nature of spacetime as a construct that both enables and limits our understanding. On smaller scales, the relationship between time and space becomes even more intricate. Quantum mechanics reveals that particles can exist in superpositions, occupying multiple states simultaneously until observed. This phenomenon challenges classical notions of causality and time, suggesting that the flow of time might not be as linear or deterministic as it appears. Experiments with quantum entanglement, where particles remain connected across vast distances, further blur the boundaries between space and time. These discoveries hint at a deeper, more interconnected reality, one where space-time itself might emerge from more fundamental principles. The quest to unify general relativity with quantum mechanics is one of the most ambitious endeavors in physics. Theories like string theory propose that spacetime is not continuous but composed of tiny, vibrating strings that define the behavior of particles and forces. In this framework, spacetime's dimensions could extend beyond the familiar four, encompassing hidden dimensions that influence the observable universe in subtle ways. Though still theoretical, these ideas expand our understanding of what spacetime could be, inviting us to reconsider the very fabric of reality. As we explore these frontiers, we are reminded of the human spirit's resilience and curiosity. Each question about time and space leads to new avenues of inquiry, new technologies, and new ways of thinking about existence. The interplay of relativity, quantum mechanics, and cosmology reflects our determination to uncover the universe's secrets, no matter how complex or elusive they may be. In this journey, spacetime serves as both a guide and a challenge. It reveals the universe's beauty and intricacy while reminding us of our limitations. The more we learn, the more we realize how much remains unknown, a humbling and inspiring truth that fuels our exploration. Time and space, as defined by relativity, are not just scientific concepts, they are profound reflections of the universe's order and mystery, waiting to be understood. The intricate relationship between time and space defined by relativity becomes even more fascinating when we delve into its implications for advanced concepts in space exploration and technology. Consider the idea of interstellar travel, a dream that has captured human imagination for generations. The vast distances between stars, measured in light years, present a nearly insurmountable challenge using current propulsion methods. However, relativity offers intriguing possibilities that could redefine our approach to crossing these cosmic gulfs. One such possibility involves warp drives, a concept inspired by Einstein's equations and expanded upon by physicist Miguel Alcubierre. A warp drive would theoretically compress spacetime in front of a spacecraft while expanding it behind, effectively allowing the vessel to move faster than light without violating the laws of physics. Instead of the spacecraft itself traveling at superluminal speeds, the spacetime bubble it creates would move, carrying the spacecraft along with it. This concept leverages the flexibility of spacetime described by general relativity, offering a tantalizing glimpse into a future where distant stars could be within reach. Another potential application of relativity lies in the use of wormholes, shortcuts through spacetime that connect distant points. Wormholes, also known as Einstein-Rosen bridges, are theoretical constructs predicted by the equations of general relativity. If they exist, they could provide a way to bypass the vast distances of space, enabling instantaneous travel between far-flung locations. However, the stability of wormholes remains a significant hurdle. To prevent them from collapsing, exotic matter with negative energy density would be required, a substance that, to date, exists only in theory. Even without these speculative technologies, the principles of relativity are already shaping our exploration of the cosmos. Spacecraft that venture beyond Earth's orbit must account for the effects of relativistic time dilation, especially during long-duration missions. For example, the planned journey to Mars, while not relativistic in speed, will still involve minor time dilation effects due to the spacecraft's velocity and distance from Earth's gravity. These effects, though small, are measurable and must be considered in mission planning. Furthermore, relativity has practical applications in navigation and communication. The Deep Space Network, which maintains communication with distant probes like Voyager and the James Webb Space Telescope, relies on precise timing and an understanding of relativistic effects. Signals sent to and from these spacecraft travel vast distances, and the curvature of spacetime caused by massive celestial bodies can affect their paths. By incorporating relativistic corrections, engineers ensure that these signals arrive accurately, enabling groundbreaking discoveries about the universe. Relativity also plays a role in our understanding of cosmic phenomena. Black holes, perhaps the most dramatic examples of spacetime's curvature, challenge our perceptions of time, space, and reality itself. Near the event horizon of a black hole, gravitational time dilation becomes so extreme that time virtually stands still relative to an outside observer. This effect, while mind-bending, has been observed indirectly through the study of accretion disks, rings of superheated matter spiraling into a black hole. The radiation emitted by these disks provides insights into the black hole's properties, including its mass, spin, and gravitational pull. The study of black holes has also led to groundbreaking theories about the nature of spacetime at its limits. For instance, the concept of Hawking radiation, proposed by physicist Stephen Hawking, suggests that black holes can emit particles and gradually lose mass over time. This phenomenon arises from the interaction between quantum mechanics and general relativity, highlighting the need for a unified theory that reconciles these two pillars of physics. Understanding Hawking radiation could provide clues about the ultimate fate of black holes and the information they contain, further deepening our comprehension of spacetime. On a cosmic scale, the interplay of time and space shapes the evolution of the universe itself. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, reveal that spacetime has been expanding since the universe's inception. This expansion, initially rapid during a period known as cosmic inflation, has slowed over billions of years, only to accelerate again due to the mysterious force of dark energy. Dark energy, which makes up approximately 68% of the universe, remains one of the greatest mysteries in modern physics. Its influence on spacetime not only drives the expansion of the universe but also raises profound questions about its ultimate destiny. The study of spacetime also intersects with the search for extraterrestrial life. If intelligent civilizations exist elsewhere in the galaxy, they would likely face the same relativistic constraints as we do. This raises intriguing questions about the nature of interstellar communication and travel. Would advanced civilizations develop technologies to circumvent relativistic limits, such as wormholes or warp drives? Or would they focus on transmitting information rather than physical travel, using signals that account for the delays caused by the finite speed of light? These questions underscore the profound interconnectedness of time, space, and the search for meaning in the universe. Relativity, while deeply technical in its mathematical formulation, ultimately speaks to universal human concerns: the desire to understand our place in the cosmos, the yearning to explore, and the quest to overcome the limits imposed by our environment. Each discovery, whether theoretical or observational, brings us closer to answering these questions, even as it reveals new layers of complexity. As we continue to probe the mysteries of time and space, we are reminded of the profound humility that comes with scientific exploration. The universe, with its vastness and intricacy, challenges our preconceptions and expands our horizons. Relativity, as both a framework and a philosophy, invites us to see the cosmos not as a static backdrop but as a dynamic, ever-changing entity that we are privileged to study. This journey is far from over. Each new observation, whether from a ground-based telescope or a spacecraft traveling through the void, adds to our understanding of the spacetime tapestry. And as we gaze into the night sky, we are reminded that the interplay of time and space is not just a scientific concept but a poetic reflection of the universe's grandeur, a reminder that we are part of a story that spans both the infinitesimal and the infinite. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.